Hello there, I'm Jerry Walsh and I want to welcome you to Racer Walsh Company here in Jacksonville, Florida. We're going to do a home video from hell today and see if we can learn a little bit about the 2300 engine. So come on in and we'll give you a view of the shop and get into the engine building. We're here in Jacksonville, Florida. That's about an hour north of Daytona, hour and a half north of Orlando. We're on the Atlantic Ocean in the northeast corner of Florida. If you're ever in the area, come on in and visit us. We'd love to have you. We have visitors from all over the world. Come on in, we'll show you the showroom and shop. Over on the right is the office area. Linda Logan slaving away. And over here we have not too much of a showroom. Most of our business is done by mail order. V8 engine, selection of the parts that we have. Back here is the packing and shipping, and Brian, who's handling the camera, also is back in the office area. This is Paul and Scott, but we'll have to talk to them later. They're taking orders. Come on back. Okay. This is the shop area in the warehouse where we keep all the parts. We also keep our own race cars here. We have 4 race cars in the shop now. This is an American sedan 302 V8 Mustang, Holly 600 Edelbrock Performer manifold. Runs in SCCA road racing. Our forklift with a crate motor going out the door this afternoon. And over here is a 4-cylinder ITB Mustang. Also does road racing and endurance racing. We'll swing around on that and take a look. These are some of the parts. These are all 4-cylinder parts. Actually, we keep a good stock Wiseco, Crower, Mallory stuff. You can pan down there if you want. We've got a bunch of motors here we're going to look at a little bit. This is a 4-cylinder Mustang, runs in endurance races. It's got a 2300 in it right now. We use it to test parts. The races it runs in are an hour and a half, 2-hour races. So it gives us a pretty good idea of how things are going to hold up, and over the course of the season how they hold up, from engine pieces to brake parts. Back here we have one more kind of unusual car. This is Academy Award winning. All right, now we have the mic hook back up again. This is a car that would run in the Daytona 24-hour or the Sebring 12-hour type race, a world sports car. This is the back of Bobby Rahall's Indy car. It's in our shop as a kind of a curiosity. It's being powered by a Mustang late model 4.6 4-valve engine, which is over on the stand over there. We're most curious about the engine, and it's an optimistic project. If it ever actually races, we'll be curious. It's not our shop's project. We're just renting out the space. And back here, buried in the corner, is a Pinto that's been in the family for a long time. Brian owns it now. I drove it a long time ago. He bought it back and is racing it currently. It's a 2300 Pinto, seen a lot of miles, still in one piece. It'll run in vintage and endurance races as well, fitted with a 2300 engine. We'll get it out of the shop come spring of '99, and it'll be racing again. Okay, we're all set up and ready to go. We've got Brian Walsh behind the camera, and Paul Bond, who actually does most of our engine assembly, is standing by here holding the lights. So we'll take a shot at it here. We're dealing with the Ford 2300 overhead cam engine, made in the United States in Lima, Ohio. But before we get started on it, we want to call attention to one other engine, which is the Pinto 2000 engine, and that is identified by 3 cam towers. The Pinto 2000 came in the Pinto in 1971 through 1974, also came in the Capri. It's made in Germany. 3 cam towers. That is not the engine we're going to deal with, but we're going to refer to it every so often through the talk here. But sometimes there's a little confusion, and we'll get to that. So Paul, you want to yank this out? We'll get that out of here. The engine we're dealing with is the 2300. It'll always have 4 cam towers. The 2300 came in the Pinto in 1974 to 1980. Came in the Mustang II from 74 to 78. Came in the Fox-bodied Mustangs, which would be like the race cars you just looked at, from 1974 till the late 80s, 88 or 89, we think was the last year that they were in there. It also came in the Capri II, using the American engine, and came in the Merkur, again a German car with the 2300 in it. Also came in turbocharged form in the Thunderbird and the Cougar, and it is also in the Ford Ranger. Now we mentioned the Pinto 2000 because there's sometimes some confusion. It comes in the Ranger in 2300 form, and it also comes in the Ranger as a 2000 cc engine. And that is nothing more than a 2300 engine with small bore, small pistons. So it's basically the same engine, small pistons. Sometimes that gets confused. It also is a 2500 cc in the Ranger, and that's done with a different crankshaft. So that's a basic overview of the 2300 blocks. Generally, all of the blocks are the same. There's no advantage to one 2300 block over the other. The turbocharged blocks aren't any better metal content than anything else. The crankshafts are also all the same quality. There's no better crankshaft than the turbocharged engine. The connecting rods on all of these are the same quality. There's no difference all the way through. There's a slight difference in the very early 74s. The connecting rods didn't have an oil hole in them, which actually made them a little more desirable for racing. But then after about, I think it was 76, they all have an oiling hole in the connecting rod. So I wouldn't even worry about that or deal with that. We're going to show you the differences that are in the blocks as they may affect your choice, and we're going to go through an engine rebuild. Assuming that you're going to put this in a mini stock, or maybe you're going to rebuild your own personal engine, and how we would do it here. We've dragged our engine shop is 2 miles away from here, and we've managed to drag 16 blocks over here to give you an example of differences between the different blocks. Now we're going to go over the differences in the blocks. They're all basically the same with a few minor differences. So assuming that you get an engine, say from the junkyard, or you're rebuilding your own engine, if you have a choice, you want one to match the car that it's going into. The early Pintos and the Mustang II were a front sump, which meant that the pan on the oil pan had the low part in the front, and virtually all of the other cars that we mentioned, the later model Mustangs, Thunderbirds, Cougars, all the rest of them, were rear sump. The low part of the sump is to the back. The reason that that's important is because there are 2 dipstick hole locations, and you want to have the right dipstick hole for the use that you're going to have. If you were to get an engine from us, we drill both the front and rear holes. We have a fixture to do that, and so it wouldn't really be a problem. But if you're having the block done locally, you at least want to make sure that that matches. So unless it was a Pinto or a Mustang II, it's going to be a rear sump, and this hole will be drilled out. This block, if we find out, is headed to Brian Spino, so it's just a front sump, and we see it didn't get drilled out. But that would be the one difference there. The other thing is, what's next? The rear seal. We have 2 blocks here. One has a 2-piece rear seal, and the later version has a 1-piece rear seal. It can be, and the year was at 85?
85, yeah.
85 and up went to the one-piece rear seal. This seal also is the same rear seal that's used on a 302, a 5-liter late model, so just in case you need one. The two-piece rear seal, it has an extra piece in the rear main, and the seal will fit into that groove on the rear main. On the one-piece seal, that isn't here, and the seal just goes straight in from the back, just like that. And we'll get back to how that's installed later on. But those are the two main differences between the early block and the late block. There's no great advantage one way or the other over one seal over the other. It's just a matter of knowing. Now, what most machine shops do and what we do is if you had a crankshaft from the early seal, it has a slinger on the back of it. Just a slinger, what do you call that? Just an extra ring that's cast onto the crankshaft, and most engine shops will just cut that off so that the crank can be used in either block. And any crank that would come out of our shop would have that cut off so that it could be used in either block. Okay, all right, we've covered the seals. 85 and later generally has the one-piece seal, and those years are not always locked in stone. Sometimes the years will be off a little bit from Ford. They move them back and forth. The other difference is the 92. 92 and later blocks generally have a small main bearing on the crankshaft. The crankshaft main bearing is smaller. This would be your 92 and later blocks, all three of these, and if you put a caliper in there, you would find that it measures just around 2.4, and if you went to the larger main journal block, it would measure at around 2.6. We're pretty close. So that's your differences. The 92 and later blocks have the small main journal, and you're going to have a crankshaft that matches that. There's also a difference in the main bearings, and we'll show you that in a minute. So those are the two differences in journal size. There's one other difference, and out of all of these blocks, we did not have a turbo block, so we're going to bring you over here. We dragged a crate engine out. This is the new turbo block from Ford, just to show you that on the exhaust side of the engine, which would be the passenger side of the engine, on a standard block, you just have your regular engine mounts, bolts, but on a turbo block, and we're not going to take this thing out of the Cosmoline, you have your engine mounts here, just like here, but it has a drain back for the oil to drain back from the turbo, and it goes into the oil pan through this drain back that's cast into it. It's not really critical if you had a turbo. You could certainly weld a fitting onto the side of the oil pan and just run a tube down into the oil pan. It's not under pressure. It's just a drain back hole, but if you have a turbo, that makes it a little nicer, and that would be the difference there. There's one other thing to mention is the fuel injection and water and mechanical fuel pump difference. And we'll go back to this block. If it was fuel injected, this is where the fuel pump picks up off of a cam in the auxiliary shaft, and if it was on a mechanical fuel pump, the fuel pump mounts right here on the earlier models. On the later models, which is fuel injection, has an electric pump back in the trunk. This is solid. There's no hole there. If you were to get a block from us, we would also drill that out, and so that it could go both ways. And we have we have a block-off plate that we sell that could cover it, so you could call that either way if you ordered an engine that you had to use a mechanical fuel pump, say for your racing class. That's basically all of the blocks. Those are the differences between the blocks. Just the seals, the main bearing size, and the oil drain back for the turbo. Otherwise, they're all pretty much the same. Okay, what's next? We're going to talk about oiling and the general cleaning up of the motor. Assuming that you get the engine out of a junkyard or whatever, or buy one used, you want an engine that hasn't been hit in the front and been in an accident, I would just reject it. And as you tear down this engine, take it apart, you want an engine that hasn't been through some trauma. You don't want an engine that's melted a connecting rod onto the crank, and you don't want an engine that's melted a piston into the bore, or has got a badly blown head gasket, or has gone through some difficulty. You just want a nice worn-out motor. That would be just fine. You'll send that to the engine shop, and they're going to clean it, acid dip it, and then bore it to the pistons, and we'll get into that a little bit later. We're going to explain, as far as sending it to the engine shop, you pretty much give them something that looks like this, and they're going to take the two plugs. There are two main oil galleys that go fore and aft in the engine, and there's two plugs here, and there's two matching plugs on the back of the block, just like these two over here. They're metric plugs, and those are your main oil galleys back and forth in the motor. You might let the engine shop take those plugs out. They're very difficult to get out. They're metric plugs, so don't lose them. You're going to have trouble finding them to get them back in again. We usually have to heat up around them and then chill the plug in order to get it out. And we have long brushes that we clean in here to make sure it's all clean after the thing has been hot tanked, and get everything looking right here if it's an old crudded up motor. We're going to explain how the general oiling goes through on the motor right now, and just go into a few points that you'll be able to deal with when you get the engine back from the shop. And I hope we're not going too fast, but we're new at this, so we don't know. This engine is upside down. This engine is right side up. Cylinder head's going to go on here. Here's a bare block upside down, and your oil pump mounts right here. The pickup is here. This would have been a rear sump pan. If it was a front sump, the pickup would be up here, and the lump on the pan would be to the front. This is the front of both motors. Now we'll go back over to this engine, and just so you get an idea, a feel for how the oil flows through the motor. This would mount again up on the bottom, two bolts bolted onto the bottom of the block, just like over there. And from here, there's a shaft that goes in here where the distributor mounts, and it's going to go into the oil pump. And that's going to turn the oil pump. The distributor, or the bottom of the distributor, which mounts into this hole, actually turns the shaft and turns the oil pump, which then pumps oil up into this first galley here, and it's going to take it out to the oil filter first. Now the shaft is the auxiliary shaft, which is right here, and that will go into this hole here, and that shaft is going to be driven by the auxiliary gear, by the timing belt that goes around on the engine. We should mention that if you don't have this piece in here, the engine will start and it will have no oil pressure. Nothing will pump oil through the motor. Got to have it. Engine would run great. You'll destroy the engine right away. Have we ever seen it happen? Well, yes, we have. Where were we from there? The oil goes out of the pump. It's going to fill up this fore-aft galley. It goes through to the oil filter, and it comes out on the outside hole of the oil filter. This hole right here would fill up the filter and then go back into the engine through the center hole. From there, it goes to the second galley, and it's going to feed oil down into the main bearings, and also feed oil to the oil pressure pickup right here where your gauge picks up, and through this hole come up into the cylinder head, run across the cylinder head, and feed the camshaft and everything, which we don't have on right now. While we're at this point, sometimes guys who race use remote filters. Rather than because of ease of getting to it or the chassis or whatever, they'll run a remote filter, and they'll put on a fitting like this in place of where the oil filter spins on. And we just want to go over one thing that we see a lot of people make mistakes on. Now, let's see if we get it on there. Again, the oil came from the outside, and it's going to go back in through the inside. Now, this is marked, we'll leave it here. This is marked out, and this is marked in. There's in cast here, and this out cast on the other side. So out goes to the remote filter, which you got to have mounted on the chassis. Out goes to in. And then from here, out from here, goes to in on the block. Out goes to in, out goes to in. If you have these mixed up, which a lot of people mix up, you will not get any oil pressure. It will stop oiling to the motor. Again, the motor will start, oil won't go anywhere. It'll be stopped right here in the system. If you were to run an oil cooler, you would go out from the block, into the remote filter, filter the oil, out of this remote filter to the oil cooler, wherever you have it mounted, up on the airstream. From the oil cooler, run it back into the engine. So that would be the way that you'd mount a filter as well. Out to in. Okay. We've never done that wrong here either, trust me. Okay, next we're going to take a look at fitting a set of main bearings and putting the crank in and checking the crankshaft clearances, the crankshaft to main journal clearances, and we're going to use the plastic gauge to do that. Before we do that, I'll just show you a little bit about the main bearings, and there happens to be a slight difference between the years depending on the crank journal size. On the earlier crankshaft, the center main bearing, or on both crankshafts, the center main bearing controls the forward and aft thrust of the crankshaft, or the forward and aft movement of the crankshaft. On the early years, the center main looks different than the other mains, and that has a side piece to it, and that's what keeps the crank from moving forward and backwards. Both the upper and lower have the same look to them. On the later, the 92 and later, the small journal crankshaft, only the side that's nearest to the engine block has this, and the other side, which is going to sit like that, doesn't have the thrust on it. So when guys get bearing sets from us, sometimes I think they got the wrong bearing set. But on this particular engine, that's the way it works. This is a late model, small journal crank, 92 and later. When you fit the bearings, you're going to wipe this clean, don't put anything on these surfaces. This is metal to metal. And the bearing is very soft. If you were to even gouge it with your fingernail, you could. So treat it gently. It has a tang on one side, and it's important that tang should fit in there. And that fit is nice and snug. And once we get it in there, just tap it with a plastic hammer or the back of a plastic screwdriver or something like that. Make sure that it's nice and even. Now these are all dry. We haven't put oil into them. I'm going to lay the crankshaft in, and we're going to put a main cap on, and we're going to plastic gauge to check the clearance between the crank and the bearings. It's a 5 main bearing engine. Now, plastic gauge is available from any auto parts store. If you can't find any, send us $5. We'll send you a section of plastic gauge. It'll last your lifetime here. This is what you would get. It's a paper envelope, and inside is a very small piece of plastic, I guess you'd call it rod or whatever. You just have to break off a little piece, and you're just going to put it across the main journal. I don't know if you can get in on that, Bri, and see that. Just lay it on there like that. And then we've already put the top main cap on this number 2 journal, which we're going to use, and you would just lay it on, and then we would torque that down. These torque down to 80 pounds. And the arrows, there are arrows on all the mains. We only have this one on so far. The arrows all point to the front of the engine. And we torque them down using a good torque wrench, but we won't go into that. Now, we cheated a little bit. When the camera was off, we already torqued down the number 1, and it has distorted the plastic piece. And if you can see the difference, go back to how small that is, and you can see how the piece of plastic is flattened out because when we torque this down. Now, on a race engine, on a street engine, you're looking usually for about 1/1000th bearing clearance. That's the difference between the OD of the crankshaft and the crush ID of the two bearings. Now, you just put your gauge up here and put it across the piece, and this is more than one, and it looks like 1.5 thousandths and not quite 2 thousandths. So that's a very simple way to test your bearing clearance. On a street engine, you will be looking for 1 thousandths, and on a race engine, 1.5 thousandths is ideal. You can go up to 2.5 thousandths bearing clearance, but after that, you'll start to beat the bearings out pretty fast. We think that 1.5 is your best bearing clearance for this for the 2300s. Now the crank has not been spun in this. We're going to take it back out again, and on this other engine we have torqued the crank in, and we oiled it. Wait a minute, let me go back and show you how to oil it. We'll just lift this out. Do we have an oiling can here? No, we don't. All right. Just lay some oil right into the bearings. That's all you have to do, and into the top bearing as well. Just smear it with your finger, and then smear it and then cover the top bearing as well. And you can lay the crank in. Now I'm going to go over to the other engine. As you torque down these bearings, you would start from the center and just do it in a sequence. I think that the book calls for 40 pounds, 60 pounds, and then finally up to 80 pounds. We oil the threads on the main bearing bolts as well with regular 30-weight engine oil. Whatever you're putting it together with is fine. And as you're torquing it down, you can spin the crank. I've already put something on here, so I can't tell. You spin the crank, and you'll see it should always spin nice and smooth and easily. It should have no high spots or no hard spots on it as you turn it over. This crank has been torqued down, and it really spins smoothly all the way through its cycle. If you have any high spots, you're going to find out why. You loosen each one in sequence, and you find out which main bearing is causing the problem. This is the heart of your motor, so you want to make sure that you get this right. This should be a nice, happy part that's just spinning perfectly. Now, as we said before, the center main bearing handles the fore and aft thrust of the engine. So I've put a dial indicator on this on the front of the engine, and we're going to show you how to check the thrust limit of the motor anyway. And I'll set that dial. I just set up a dial indicator. And what we do is just get a good size screwdriver, just get it in on the crank and just push it forward, and then go on the other side and push it the other way, and your dial indicator will move and tell you how much fore and aft movement that you have on it. Not very difficult at all, just like that, back and forth. This crank is showing 4 thousandths or 5 thousandths movement, and the limit, according to the book, is between 4 thousandths and 10 thousandths, and the outside service limit is 14 thousandths. In the 25 years we've been doing these things, I've never seen a 2300 crank that has a problem with thrust, unless the center main has been destroyed in heat or something like that. So it's not really something you have to worry about too much, but we want to show it to you anyway. Okay, that we're finished putting the crank in, and we still have not final assembled this motor. We're still just putting it in so that we can check things, but we did oil the crank and we did torque it down. Now we're going to just place a piston into the number 1 cylinder here, and we're going to find top dead center on this motor. We're still not into final assembly. We're just going to put it together. So we'll shut off the camera for a minute. Okay, we're going to the next part, which would be we've oiled the main bearings and we have the crank spinning, and now we're not going to show it, but you would put a rod. Connecting rod and piston assembly up, and we don't even have rings on this. We're still mocking this up. We've just slipped them together, and you're just going to put it up in the bore, and you could do the plastic gauge on all of your rod bearings. First the 1 and 2, and then you could spin the crank over and do 1 and 4, and then you could do 2 and 3 after that. Now we're going to put the number 1 rod and piston assembly in. Paul has put a protective caps over this that, again, most auto supply stores have. If you don't have that, you can get a piece of plastic hose, or you can be real careful if you want to put it on. we have oil on the bearing here, and we're just going to put this in, and we're going to try to find top dead center and check a few other clearances on it. Sometimes a little awkward, and it's fun, but easier to have a friend sort of help you and kind of aim it up here. But so that now that the cap is up against the rod bearing, I'm going to take the protective boots off and hang on. And where is it? Here it is. Okay. Remember, on rod bearings, the tang on the top goes on the same side as the tang on the bearing. It's always tang to tang on these things. That's on the mains and the rods both. That's in there nice, and we're gonna shut the camera off for a second, and we're gonna just torque these down so that they're torqued up right, and then we'll come right back. Okay, we've torqued down the rod cap now, and what we're going to check here is the rod side clearance. That's the slop that it has in the between the side thrust faces of the crank journal here. And normally on a street engine it would be 10 to 15, all right, and on a race engine we like about 15 to 20, a little more side clearance in there. And what you do is just keep fitting feeler gauges in here until you can't get any in, and that'll tell you what your side clearance is. This one is 15, so we're gonna leave it the way it is. We just checked that. So that's rod side clearance. It's really not that critical. We've really run some much larger rod side clearances. If you have really a lot of side clearance, you're just going to lose oil pressure. The oil will come out of there easier. In a race engine, it's not too critical, but it's nice to have it right if you can. So now we're going to turn the block over, and we're going to try to find top dead center in it. And so I don't have any rings on this piston. This thing's going to slide all over the place probably on us, yeah. Piston comes up to top dead center. And a zero deck piston would be one that is absolutely even with the deck. You can run pistons 7 thousandths out of the hole and still get away with it. After that, you're in danger of hitting the cylinder head. So that's about the most I would take a flat top piston out of the hole. This has valve reliefs for big valves. It's a Wiseco piston, and we're going to put the lower pulleys on and do some timing on this, and we'll show you that. So we're going to shut off the. Okay, we've spent about the last 20 minutes here fitting the keyway to the front of the crankshaft, and it's worthwhile to spend some time to get all this stuff to go together right. And we put the front cover on. We put a new seal in there. You just tap the seal in. We oiled the seal, and it fits onto the front snout of the crank. After that, we put the lower crank belt pulley on. It has a beveled edge which goes against the crankshaft, and the flat edge goes forward. And then we put the belt guide on. The guide is also curved, and you want it to curve out like this, so this will keep the belt from going forward. There's another belt guide on the camshaft, which is not on the engine yet, and that keeps it from going backwards, so we'll show that a little later. So we put the lower gear on, and then we put our 4-inch aluminum pulley. This is a single belt pulley. Now, also went to the hardware store and picked up a 6mm bolt that I just threaded in there, and I cut it off and ground it to a point. And this is going to be our pointer, and this is a good solid piece. I know that most 2300s pick up their timing pointer off of the timing cover, but if you're going to run a race engine, this is the way to do it. It's to find top dead center. So you're going to have to make up something like this that fits or suits your application. We dropped the bolt here. Okay. This is a top dead tool we call the world famous combo tool here. You'll see one of its uses. And this isn't rocket science. This is just anything to keep the piston from coming all the way up to the top, and we'll show you its function in a minute. We've got 2 holes drilled and a little hole here, and I've just put a bolt through it so it won't come all the way up. These bolts are probably going to be the hardest to find. They're 12 by 175 by 30mm bolts, and we got to get stainless bolts to do this thing. It cost a fortune. But you could just use your regular head bolt and use a lot of washers and use a piece of angle iron, drill a hole through it, just anything to keep the piston from coming up. And you want to have a good solid source here. So we're going to tighten that down, and I'm going to put a wrench on that. And then we're going to show you this kind of neat tool that's specifically made for the 2300 and specifically for holding a degree wheel. This will screw into the front of the crank, and we're going to have to shut off the tape for a minute, and I'm going to just tighten this up. We'll put something in between the crank and the block so we can get that good and tight so it can turn it both ways. And then the degree wheel, which can spin separately on the front of this, is going to screw in. Put that on there like that, and allow us to turn the crank and then separately turn this wheel so that we can get our final setting. So we're going to shut off for just 1 minute, and we're going to tighten this up. Just tighten this bolt against the front of the crank snout so that we can turn it without having it come loose. So. Okay, we have tightened up this main bolt onto the crankshaft here so that we can turn the engine forwards and backwards and get that piston to come up against the stop, and it won't come loose. So that's all set here. Now, I should mention that if you had the cylinder head on, we made a little tool. You could just knock the center out of a spark plug, and we put a bolt in here and rounded it off, and you can, if you had the cylinder head on, you could you epoxy this bolt in here. You could make your own tools that you could do this with the cylinder head on as well, and that's just another way. Just take a spark plug and epoxy a long bolt in there so it'll hit the spark plug, or hit the piston and keep it from coming all the way up. Don't forget to take it out when you start the engine. Okay, now this is the hard part now, but it's really not that hard. What we've done, and I'm going to go to the front, and you almost don't even need this degree wheel for what we're doing here with a positive stop method. But if you notice, here is TDC as it would show, and I've loosened the front here and spun the wheel around. And if you read this here, it shows 35 degrees where the wire is just pointed to. And then if you spin it around the other way, it's 35 degrees as well on the other side. What that means is when we take the positive stop off and this wire goes to TDC, that's going to be true top dead center as far as this degree wheel shows. Secondarily, we've marked the front pulley at one stop right here, and then we turned it all the way around and mark the pulley again here. So we'll bring it all the way back again. Now halfway between these 2 points is going to be top dead center. And why do you have to measure this? Because when you get the piston right up to the top, you can't really tell. There's about a 6 or 8 degrees in there where it looks like it's at the top, but you're not sure exactly where it's at top dead center. So this will tell us exactly where it is. Now what I do is just take a piece of paper. You mark where your 2 marks are. Fold the paper over. That's halfway in between them, and this point right here is going to be top dead center. And I lost my Sharpie here. Let's see. Paul, you give me a hand on this, and we'll just hold that down, and pull it towards you a little bit. Okay. And that's your mark. That's going to be top dead center. Now, theoretically, we could take these off. This is like Houdini, letting the woman out of the cell. All right, and when we bring that up to top dead center, this should also be TDC on the front, and as it is. And from now on, we're just going to bring that to top dead center. We're going to chisel a mark right in there right now. We'll bring this to top dead center, and then we'll just bring a wire onto this timing wheel and get it to top dead center, and that will be our reference for this engine when we do the cam timing. So that becomes a very important point for this engine for the rest of its life, as long as we're using this pulley on this crankshaft. So we're set with that, and we're going to do a chisel punch on there to mark it. So that's top dead center, and that's all you got to know about it.
Okay, having found top dead center on the motor, we've taken the piston out of the engine. We're still mocking it up for a fit, and we're going to show you how to do ring end gap and try to explain a little bit about getting rings on pistons. The end gap is the space between the ends of the piston rings as they're fitted inside the engine on the piston. They vary depending on the piston used and on the ring used, and the racing pistons that we sell, which are usually a thinner ring, a 1/16 inch double molly ring, they come oversized. So if this was a 30 over bore, 30 thousandths over bore, the rings are actually made 35 thousandths. They're made that way so that you can grind them down to get an exact fit. The different piston and different ring combinations call for different end gaps, and I'm just going to generalize on this because there are too many variables here. A stock piston and ring setup from Ford would call for anything between a 10 and 20 thousandths end gap, and if you used a standard ring, it would not be an oversized ring, so you probably would not have to file it down. If you're running the racing pistons where you get a 035 ring, you would have to file them down. That would be for, say, the Keith Black or the Wiseco's with this thin ring. For the Wiseco, we call for a 19 thousandths top ring and a 15 thousandths second ring end gap. The Keith Black calls for a much larger 30 thousandths top ring, and again a 13 thousandths second ring. Those are in the instructions with the rings, so that's not too critical. We have a real basic machine here in the shop that a lot of guys have in their home shops to end gap the rings. It's available through a lot of performance shops and stuff. You just place the ring in the gap, and this is in the top here, and this is the grinding wheel. You squeeze it down, turn it like this, and that'll grind the ring for you. And you take a little flat file and just clean up the sharp edges on all four sides, on both sides of the ring, and that will take any burrs off of them. Only takes a few shots there. Then you place the ring back into the bore, and hopefully this is showing your end gap here. I've taken that piston. See how good I am at this. And you can use this just to square the ring into the bore, and just with your fingers even to the top of the bore. I could have done a little better on that one. I'd check it again. And you can hopefully get down in there. Put your feeler gauge in between the two ends and keep checking it. Take it back out, file it a little more, push it back in again. This one we've already end gapped to the 19 thousandths. It's a top ring, so that would be okay. Whoops, there we go. It's dangerous around here. It's a time-consuming process. It takes a while to end gap all the rings on a race engine. That's where they cost a little bit more money. Now, when you would assemble a ring onto the piston, we're a little bit out of sequence here, but we'll go ahead and show it now anyway. You would probably want to have the rod on the piston, and this rod still doesn't even have wristband clips on it. The oil ring is a three-piece, and it's well explained in the instructions for from the ring manufacturer. But you can just slide them on, and they sort of you see how they fit into the lower groove and the upper groove on the oil ring part, and we're confident that'll make sense. We really don't think we can show it. It's sort of like feel on that. When the ring is placed on the piston, the the gaps for the oil ring would look like this, assuming that the front of the engine is that way. The gap on the center part of the oil ring, it's a three-piece oil ring, is straight to the back. The one side is off about 10 degrees from the straight back, and the top part of this is 10 degrees. The gap on that one is 10 degrees the other way. On the compression ring, the second and first ring, if this is towards the front of the engine, one is off about 10 degrees to the left, and the other one, doesn't matter which one, is about 10 degrees off to the right. That's according to the Ford manual. That's the way they do it for all of their rings, so I think that would be good. Who knows why that works, but that's their recommendation, so we'll go with it. To put a ring into the piston, there are a number of different tools. This is a fairly simple tool that will expand the ring, and it's a little difficult. Let me see if I can do it this way. A little bit difficult to work with, but that'll pull the ring out, and you can slide it down over the piston. Or another way is to that showing up all right? Is to just hold the ring like this, slide it around, then grab onto the ring, your finger here, and pull it down. You would start with the second ring and then work up to the top one. First do the oil ring, then do the second ring, and then work up to the top one. And that ring is in there. It's important, obviously, to get the right rings that match the piston, because there are different thickness rings. Generally, race rings are thinner. They have what's called less ring flutter. Who knows how they figure out whether they're fluttering when they're flying around in there. But you want to make sure you got the right rings with the right pistons. Now I'm going to try to get this back off without busting the ring. Okay, there we go. And while I'm on the subject, if you have a dome piston or any piston like this, before you put the piston in, it's good to just run a little crocus cloth and take the sharp edges off of these corners. And this one's already smoothed out from the factory, but if you do have a piston that has a dome on it that's been machined real sharp, you want to just smooth that off. That can become a hot point when the engine is running, and they look pretty when they come out of the box, but you don't want any sharp edges on a piston here. All right. That's basically end gapping the rings and fitting them to the pistons. We're going to shut off for a minute, and we're going to get the rods all lined up, and we'll show you the rod lengths and stuff like that. Next is rod length and floating pins and press pins and all the rest of it here. We'll show you a stock Ford connecting rod, and it's a pretty ugly one, I'll have to say that, but they do not have a bushing in the big end. All pistons that come from Ford are press fit. That means that you put the wrist pin through the piston and the rod in a machine, a hydraulic press, and once it's on there for good. We'll leave that off to the side. When you get a reconditioned rod from us, this is a stock 2300 rod. We could either not, we could leave it as a press fit if you wanted, but normally we put a bronze bushing in here so that it would be a floating pin, and I'll show you that in just a second. Then we put a ARP rod bolt in it and resize the big end to make sure that it's nice and round after we've put the ARP bolts in there. This is a stock 5.2 length 2300 rod. We have a couple of other choices. We'll go through the rod choices in order of their strength, I guess. Well, doesn't quite work out right. This is a Chevy 5.7 rod. It's a longer rod. We recondition a stock Chevy 5.7. Again, we put the bushing into it, and we put the ARP bolts on and check it for roundness again, resizing the big end of it. This would be the weak point in a race engine, but it has an advantage in that it's economical and it allows you to get a long rod into the engine. I'll explain long rods in a second. The 5.7 Chevy rod, we would put a limit of 7,200 RPM on for that. After that, that becomes a liability. The next rod is the Crower. This happens to be a 5.7 example of it, but we have both the 5.7 and the 5.2 versions of it, and they can really be ordered in any length. They'll make them to order for you. Again, it comes from the factory bushed, has ARP rod bolts on it. It's really an excellent rod, has a long history of running in oval tracks all around the country in very high horsepower applications. This would be our choice for a rod, and is our choice for the rod in all of our racing engines, based on weight and strength. It's a good value. The last rod is a Ferrea rod, a different H-beam construction rod, very strong. This particular rod is headed into a turbo engine. It again comes bushed, and it's a little bit heavy in the Crower rod, but it's as strong a rod as you can get for a 2300 or for any application. Again, a very good reputation for all of these rods. Now I'm going to get them back in our length here so you can get an idea. All of the these are both 5.2 length rods, and these are the longer 5.7 length. It's a half an inch longer from the center of the rod journal to the center of the wrist pin. The pressed-on rod, as came stock from Ford, and I'll just show you what it would look like. Once it's pressed onto the piston, and it's done with a hydraulic press, sometimes they heat up the big end to get it on there. That's going to be on there for the life of this piston, and this is just fine. Every stock Ford comes like this. This is fine for a long-term rebuild, but it's not really very serviceable. If you have to take this off, you distort the end of the piston when you press it off again. Pretty much usually wreck the piston when you take it off. This is kind of a one-shot deal. If you're doing a race engine, it's a lot easier if you have a floating pin, and I should go back one more time. A pressed-on rod does not use a wrist pin clip, and as a result, pistons that are made specifically from the factory usually don't have any groove in here to hold a wrist pin clip on. You don't want to put a wrist pin clip on any pressed-on rod. The only thing that's holding this pin in place is the fact that this rod has a interference fit or onto the wrist pin. For a full floating rod, it floats in the wrist pin, and it also floats in the small end of the connecting rod. This rod would be held on by an ARP circlip, which is going to be in this envelope. We haven't gotten it out yet. I got it. These are a bare to put on, and we use two circlips on either side, and it's sort of like putting piston rings on. You sort of get it started in the groove, and just push it around and get it in. We use a real small screwdriver that we have a little notch on, and there's nothing real pleasant about getting wrist pin clips in. But the advantage of that is that you can service either the connecting rod or the piston easily. If you have a problem with a connecting rod or something like that, you get the piston back off either way. So it's as simple as taking the wrist pin clip back out and changing the rod again, or taking it off of the rod and piston. There are different length wrist pins, and we also have different diameter wrist pins based on the connecting rods. Chevys use 927s wrist pins, and Fords traditionally use 912, but there's a mix and match as the industry has gone on, so you want to make sure that you have the right wrist pin size when you order your wrist pins or order your pistons and your rods, so that everything is compatible. You should know that anyway, and our catalog lists all of that stuff, but it's worth checking anyway. Also, when the clips are on the pins, this should be a nice snug fit so that the pin is not slamming up against the wrist pin clips, and that is affected by the length of the wrist pin, which is also different from piston to piston. So they kind of have to be a match set, and if you order some, write it down, keep track of it, and so that if you have to reorder another part later on, you'll get the right piece. Now the difference between the long rod, which we call a 5.7 rod, and the stock rod, a 5.2. There's your 5.2, and there's your 5.7 rod. The rod length is the same, and all that has happened is we have moved the wrist pin higher up in the piston. You have to do that, otherwise the top of the piston would, if you put this piston on this rod, it would stick out of the top of the block, smack into the head, so that won't work. That's called the compression height. That's the distance between the center of the wrist pin to the top of the piston. We sort of hold it all at a 5.7 rod. Some people run 6-inch rods. That becomes a 2-ring piston, and boy, you've really got to have got to have everything right to get that to seal. You get with the small skirt that a 5/7 rod piston has on it, you get some rocking, and you better have a good fit between the piston and the bore, or else you're not going to get sealing between the rings. We would say for a performance engine, certainly consider the longer rod, and we'll explain the advantage of the longer rod. For a street engine, we would stick with the standard rod length, so that you get the deeper skirt and the longer skirt, so that the rings are supported well in the bore, and over a period of time you won't have oiling problems on the long haul with the standard rod length. The long rod is for a competition engine that is minded to about every 20 hours of running, so that's a different deal. Now, when a long rod piston is put into the engine, you say, well, what's the advantage here? Well, one advantage is the reciprocating weight. The piston becomes lighter. There's also less rod angularity. That is, the piston never gets cocked as much as it does with a short rod, and there's less side loading on the piston as it goes through its stroke in the cylinder. The other advantage, and you really have to drink a little bourbon and try to figure this one out, but as the piston, with the long rod, the piston actually spends more time towards the top of the cylinder during the compression or during the power stroke of the engine. So we'll say from top dead center to arbitrarily, we'll say 30 degrees down in the hole, this piston with a long rod will be up here for a longer number of degrees. The result is that the force of the compression is acting on the top of the piston for a longer period of engine degrees. Theoretically, the result is more torque and more horsepower. So that's what that's all about, and that's well proven and well documented in dyno testing. So there is an advantage to having a longer rod that way. The reason the factory doesn't do it is because they want those rings to be nice and square in the bore for your 100,000-mile engine. Now, we've been talking about a long rod, and that does not change engine displacement, nor does it change engine compression ratio. This rod has it still goes down in the, as a result of the crankshaft spinning around, it goes down in the bore the same amount, comes back up to the top of the bore the same amount. The piston is still in the same location, a zero-deck piston. If we were to change to a stroker, have I covered it right now? If we change to a stroker crank, we're going to change one thing, which is the distance that the piston goes down into the hole, and equally that it comes back up to the top of the bore. Now, you have the 2300 cc crank, which is what we've all been dealing with so far, but there is also a 2500 cc crank. The difference, if you want to go to the crank here, Brian, is the difference in the distance between the center line of the crank, which would be the center of your main bearings, to the center line of the rod, which is the throw. And this goes around, this goes up and down. This is pretty basic, but we got to get it here. So as on a 2500 cc, this distance would be further out. Now, if you're going to run, everything being equal, you would have to run a shorter rod or a shorter compression height on the piston if you change the stroke of the engine. And otherwise, the piston would come out of the top of the engine. So I hope we've explained that. A stroker engine requires a different combination of piston length and compression height on the piston. So you can't just put a stroker crank in a 2300 motor without also changing either the rods or the pistons to match. And our catalog, again, will give you the choices as to the pistons that you can do with that. So hopefully that takes care of rods and pistons well. All right. Okay, just to cover our butt on this video here, we have to comment that of the 15 blocks that we have here at the shop or whatever that were dragged over from the engine shop, we noticed that the one block we're using to demonstrate did not actually clean up at 30 thousandths. Because of ring wear and piston rock, you can see this slight line up at the top where the boring didn't get rid of that. This would not be an engine we sell to a customer. The customer's engine would, this would have to go to 40 before it went out of the shop. And as we're speaking about bore, 40 is the maximum that we would go on a Ford motor. They're thin wall castings, and you can go to 60, but it's just not desirable. You start to get wall flex and everything else. 30 is ideal, is a very good selection of rings. 40 is okay, still a good selection of rings, but that's as much as we would go. You don't really get much of a compression, much of a displacement increase by boring. Look at it mainly as a way to just clean the engine up and get it fixed up. If you had an engine that we set out of the shop, as you can see, this is a nice bore finish all the way up, and that's the way they go as they go out of the shop. If an engine is bored in our shop, it is done with a torque plate bolted to it. This is the torque plate. We bolt it onto the top of the bare block and torque it down, and that theoretically would distort this engine block in the same way that it would be with the head bolted on. And so we bore it with this torque plate bolted onto it, and the theory is that the pistons, the bore will be round when the engine is in actual running trim with the cylinder head bolted on. We've duplicated the torquing of the head bolts as closely as we can that way. If you get a V8 engine from our shop, we have the torque plates for the 302s as well. So that's one advantage to getting an engine from a specialty shop. Okay. Okay, we're going to finish up on the block and talk about piston to wall clearance there on the different pistons. This is a cast piston. They're junk. You can buy them for about 20 bucks each, and they run fine, but over a period of time, as the engine wears, they're notorious for cracking at the skirt if you do any kind of RPMs on them at all. The advantage of them is that they have a low expansion rate, and they keep the rings nice and straight on the bore. They would go into a block at 1/1000th wall clearance. That's the distance between the skirt of the piston and the outside of the and the ID of the bore. Normally the bore is the same, and the difference is made up in the size of the piston by the manufacturer. But if you're going to have an engine done for you, it's better to give the machine shop your pistons and tell them what clearance you want on them as determined by us or the manufacturer, and then you'll be sure that you have them right. The next step up from the cast pistons and the choice that we would have for a street-driven vehicle or a performance vehicle that's driven on the street would be the Keith Black. It's a hyper-eutectic piston. It's a high silicone content casting, and it's the choice or what is being used on most new cars nowadays, including the late model 5.0 Mustangs and everything else. They certainly have a lot of miles racing on them as well. These go in at 2 to 2.5 wall clearance, and the disadvantage of a cast piston, no matter what it is if this piston fails, say because of detonation or you run out of fuel and start hammering on the top of the piston, it's going to shatter. And when the piston shatters, your rod is going to go through the side of the block, and it's going to eat up a block on you. That's the disadvantage. But it's still a good balance of performance and reliability against cost. If you can afford it, the next best step is the forged piston. This one's a Wiseco. You can't get any better than this. And what they do here is have an ingot of aluminum and a ram comes down and sort of like punches it into shape. And as a result, there's a grain structure, a molecular grain structure to the aluminum that makes it much stronger. This piston is a Wiseco. It's the same. You'll get the same forging that Mark Martin's running in his Winston Cup car. You can't do much better than these. They're very good quality, and these can run at 4 to 4.5 wall clearance. Any forged piston still has a higher expansion rate than the cast piston. So if you were to use these in a street engine, you'd have a little piston slap when you started it up on a cold morning until it takes about a minute, and then that piston would expand. The heat would build up in it, and it would expand up to its proper clearance in the bore.
The advantage of a forged piston is if you do have a detonation problem or a problem where you screw up on the settings on your engine, this piston would melt down rather than shatter, and as a result you very likely would be able to catch it before the rod goes through the side of the block. You could probably even salvage the block if you can figure out what's going on soon enough in the engine. So those are the three choices and the three clearances on different pistons. One other thing we didn't cover in here is the auxiliary shaft, and we're going to need those bearings. Do we have them? Okay. The auxiliary shaft again is what drives the distributor. It's run off of the timing belt, turns it off of this gear. We'll show you that in a second. It goes into the block and rides on two bearings. They're fed directly from the oil pump, the first bearings to be fed, and the bearings are right here and right here. Again, when you bought the block, these should be in good shape, or at least okay, and you're going to replace them when the engine is hot tanked or acid dipped. The bearings should be put in by a professional shop. You can't just get in there and tap them in with a hammer. That won't work, and the bearings will not last if you do it that way. We'll show you the tool when we get to a cylinder head. It's a bearing installation tool, and it's you have to have that to get those bearings in. This particular shaft was for a mechanical driven fuel pump, and it has the eccentric in here. This is higher on one side like a cam lobe, and that would drive the lever on the mechanical fuel pump that goes into this block. I'll tilt that up a little bit. Again, if you had the fuel injected block, this opening would be solid, and also the auxiliary shaft that went with it would not have this eccentric on it. So if you're mixing and matching pieces and you're going to have a mechanical fuel pump, you're going to have to have an auxiliary shaft from an older engine that has this eccentric on it. And I lost my hold down plate too. Okay, we're back again with the parts here. These are the bearings that this rides on. Again, the bearing has an oiling hole in it, and that's going to match the hole in the block, and that's what feeds that. Both of them have oiling holes in it, and the machine shop will hopefully get the holes lined up for you. The auxiliary shaft is held in by a retaining plate. Fits in here, and it's screwed onto the block by two Phillips head screws, pretty heavy-duty screws that have a star-type washer on them. When you put the auxiliary shaft on, you put that plate on, you would use blue Loctite to hold them in. Blue Loctite is a sealant that's used for the threads. They have a red Loctite which you use for a stud, but for a threaded fastening, you use the blue version. And you get a tool like this, which is something your buddies who work on their motorcycles will have. You put a Phillips head end on it, and you whack this with a hammer, and it impacts the screw in so that it'll be in there good. I would really use one of these. You can't really get it in tight enough with just a regular Phillips head screwdriver done by hand. If any of these are worn, if the shaft is worn for some reason, or this plate is worn for some reason, sometimes you have a problem where this moves forward and backwards ever so slightly, and it will cause a problem. Your distributor is interacting with that gear, and if you start stripping gears on the distributor, it's more than likely the auxiliary shaft, and more than likely that's moving forward and backwards in the block. If you do strip a gear in the distributor and you just change the distributor gear again, you put it back in, you're going to strip more gears, as historically we have found. And usually most blocks don't have the problem, but if it does, I would change the auxiliary shaft and I would change the retaining plate, and that should take care of the problem. That's always been the cure for us, is to change those two things. The belt gear well, I should say there's a cover here. It just takes a simple seal that just taps in, no big deal. Just oil the seal as you put it on the shoulder of the shaft, and then your auxiliary gear just goes on. And don't forget to put blue Loctite on this bolt as well and torque it down as to the book. And while I have the block here, we reviewed the tape. If I had that, I made a mistake here. The oil, we told you the oil comes from here and it goes up to the block to the cylinder head, and I said this is where you pick up your oil pressure. Well, that's not. That's the water temperature. The oil pressure is up on the cylinder head just above it, and we'll show you that when we put the cylinder head on. So that pretty much takes care of the basic block, and we'll shut off now and set up with the cylinder heads and go to them. All right, we're ready for cylinder head madness now, and this is we have to sort of give you an overview of cylinder heads because they're a last count cylinder heads for the 2300, and they're in so many different varieties from 74 up to the present time. A lot of things have happened, and we'll try to aim you in the right direction. I have a cheat sheet, and we're going to include this sheet that is our breakdown of the cylinder heads with the casting numbers and some information on them. And I'll just go over a general overview of them. This sheet we're happy to mail to you. It'll come with a video, and if you're watching the video and don't have it, call us up. We'll mail you one. Happy to. The earlier oval port heads were on all of the 2300s, Pintos and Mustang 2s prior to 1981, and the Mustang 3s up to 1981. That's your oval port. And this would be the intake manifold that would most likely have come with it. This carried a little two-barrel carb, 32, 36 millimeter two-barrel carb. And that would be a typical intake. It would have had an EGR plate on here and a carb on top of it. In 81 and later on the cars, they went to a D-port head. They had a, we hope you can see the heads, of course, are standing on end, but this is the bottom. And they had a fuel puddling problem for emissions, and so they went to the D-port head to sort of cut off the bottom. And this would be the intake manifold that went with them. And this is kind of a hard intake manifold to find, and a lovely example we have here. It's 81, 82, 83, we think, around those years, where you still had the two-barrel carb. Then they later went to a one-barrel carb, I think in 85 or 86. And where they still had a carburetor and had the D-port head. While we're on these particular manifolds, if you took the EGR plate that held the two-barrel carb on, we make an adapter, cast adapter plate that goes on top of them, and very popular for mini stock use. And then you would put like a Holley 350 or 500 on top of that. It's all the same pattern all the way through, but you can't just put the Holley smack onto the intake. It doesn't seal, and the linkage hits on the intake. So you need this adapter plate. We also have, and that's the most popular, the open plenum. It gives the fuel a better shot into the manifold, gives it a little more length before it gets to the engine, and that's a good thing. We also have a two-barrel version, or a two-hole version. Some tracks require a two-hole spacer plate, so that's also available. But the single hole version is the most popular. While I'm on the subject here, this manifold, the engine water or antifreeze would come out of the manifold here and exit into a heater hose through the back here. If you had gotten this from an early Pinto or early Mustang 2, there's a plate on the back of it, and you can take all the fittings out and put pipe plugs in them, but they're kind of getting hard to find. We're machining a plate up now that goes on the back of it like that. And the other way, on a race engine, you can just cut out a piece of flat stock, and it's about the same thickness as your intake gasket, and put it right in here, or weld this over if you wanted, and that would keep the hot water from getting into the manifold, so the manifold would run a little cooler and run a little better. So that's typical of these two. Now the D-port head, first it came with a carburetor, and then it went to fuel injection in 87. It went to fuel injection in the cars. And we'll get down to this. This is another fine example of a D-port fuel injection manifold. And this typically had a top piece that went over the top of the valve cover to your throttle body. and it's about what looks similar to what's in trucks nowadays. The fuel injectors sit on a rail here. They're held on with a couple of bolts that go into the manifold, and you just grab onto them, take them off like this, and we make an adapter that goes onto here, again, to take the Holley carburetor that mounts on top of that. And this is probably our most popular manifold for mini stocks right now. When you're taking the injectors off, you can either epoxy up these holes, or you can weld them shut, or you could tap them and put a pipe plug in them. It's not too difficult. The adapter goes on like this, and the carburetor just simply mounts on top of it. We usually do some grinding in here to match the intake holes to and bring these to a point so that you get a little better flow and separation as it goes into this intake. This is a better intake. They've gone to some trouble to make the two center runners longer and more evenly matched to the two end runners, which the earlier intakes really don't have. The two center runners are very short, and the two end runners are much longer. So that's why this manifold generally makes more horsepower and is the better choice. That again is a D-port fuel injection manifold. These are plentiful, and this is a popular combination. That down there. The next one is a truck cylinder heads. Most of them are round port, and with a round port like it comes on the Ranger and stuff, there aren't too many manifold choices. The Canon manifold is one. It has matching round ports, and it'll bolt on just like that. We do have another adapter for that goes the other way. This came with originally or was made to put a Pinto type 3236 two-barrel on it. But we also have an adapter that would go on there so you could put a Holley 350 or 500 onto this manifold as well. The last of the group is the dual plug head. This has, again, a unique intake pattern. It looks like the fuel injection manifold, but it's something we're not really working with on a race engine yet. There's another set of plugs on the spark plugs on the other side, which they fire not when you expect them to fire. It's an emissions type of head, and you're going to have a little trouble finding manifolds and stuff for it. So we tend to stick to any of these choices, and probably the D-port is the one that has the most options for you at this point. So, but the dual plug head is a lot of them around now. It's the later model head, so just so that you know that it exists. There's one more intake manifold that we'll mention. We're going back to the oval port, way back in the old days. This is a 1979-80 turbocharged version of the Mustang 3, the Fox body Mustang, when they first came out. We raced one of these for a few years, and I really learned to hate it, actually. The carburetor on this was, again, a little Pinto 32 millimeter, 36 millimeter. That's the size of the intakes on those things. And it draws down from the carburetor. It's mounted on the intake side. The turbo mounts here, sucks in through the turbo, and blows it into the engine right here. So it was a very compact unit. There was an exhaust on the other side, went underneath the car. The exhaust pipe had to be perfect. If it had a little crack in it, the turbo doesn't come to full boost. This was restrictor plate racing for us, if there ever was. We had to run it with this little carburetor. The best we got was right around 218, 220 horsepower sucking through that Pinto carb. That was restrictor plate racing, I think. We're getting a surprising number of customers who are rebuilding these engines, so we'll just mention it. If you were going to put a bigger carburetor on it, you would have to take the manifold off so that you could match whatever carburetor you're putting on, make these holes bigger, or else you're not really going to get much advantage of a bigger carburetor. The Holley 350, which could be put on with an adapter like this, just doesn't fit. It hits the valve cover. There is a Weber carb that has the same bolt pattern as the earlier Pinto two-barrel, and it also is a very tough fit. The valve cover's right there, and you have to really work to get it on there. You have to grind and fit on the valve cover, and there's some difficulties with the with the throttle linkage as well, but if you want to work at it, you can get one of these on, and it's a nice jump up. This is a dual 38. Let me correct this. So it's 38 millimeters and 38 millimeters as opposed to 32 and 36. It doesn't sound like much, but from a percentage increase, that's quite a bit. It's also a nice replacement carburetor for any of these other older models where you're still working with you have to work with a standard 2 early Pinto pattern on it. So.
Tell them about the newer combustion chambers.
Oh, okay, well, we'll get into that next. Okay, we'll go to combustion chamber. Okay, we're going to show the two different main differences between the combustion chamber shape on 2300s that pretty much cover all of the years. There was an open chamber that was used on the earlier engines, and then on the later engines, they went to a heart-shaped combustion chamber, identified by this would be the top of the heart right here. The later head actually promotes swirl in the combustion chamber, and this would be the head that makes more horsepower in a stock form. This happens to be a D-port head, and this is an oval port head. The D-port head with this would be one of the more desirable heads. But if you're going to put big valves in a head, you're going to have to do more work to this cylinder head than you are to the open chamber. And let me show you. When Ford SVO came out with a big valve head, they used this open chamber design because it's just easier to do. They offered a head in the SVO catalog. They don't offer them anymore, and the head never came in a production car. It was just done in the special vehicles operation. The deal is when you put big valves in, and both of these heads have had the seats taken out for the big valves, you have to unshroud the valve right on the side where it comes up closest to the edge of the combustion chamber. The reason is that you want your fuel mixture to flow into the cylinder. If it's completely shrouded, you're losing all of that effect of that part of the valve. When you take the same valve and bring it over to the closed chamber head, you can really see that's really right up against the side. And what we would do when we fit this is to take out the edge of the combustion chamber around here, so that you'll still have flow from the valve into the cylinder. We use two general grinding wheels. One is a carbide bit, and a bit like this costs about $30, but it's really the only thing to cut with. To cut metal with, and it cuts it pretty easily on a air grinder. And then we would finish it up with a cartridge wheel. This is a sandpaper cartridge wheel, and that would do your finishing up on that. When we put bigger valves in, and these valves are an undercut stainless steel valve that has a smaller diameter here to get more flow through it. And we do a 3-angle valve job. The valve job is done on the head. The cut is made on the head. The first cut is 30 degrees. Then there's a 45 degree, which is where the valve seat sits. And then you have a 60 degree, which is done inside the throat of the valve. I'm not going to go into all the black magic of porting and polishing valves, but generally you want to smooth off this edge around the inside of the valve where it crosses over, at the throat of the valve. That's going to increase your flow the best. So that would be your initial porting, and you can also thin down the valve guide as well, so that doesn't take up as much room. Okay, that'll do. Intake valve. Since an engine's an air pump, the amount of air that you're going to get past this intake is going to affect how much horsepower you make. When the exhaust valve opens, it's pushed out by pressure, so it's not quite under the same challenge as the intake is. Okay, can't think of anything else for the moment. Okay, Paul just pointed out something. On the heart-shaped combustion chamber engines, you're going to pick up about a half a point compression ratio in general over the open chamber type cylinder heads. As far as a race engine goes, compression is probably the cheapest horsepower you're going to be able to get. It's simple and it's not hard to do. People often ask us how much to mill off a head in order to increase the compression, and it's very general because there are so many different combustion chamber volumes from year to year. but generally we say you mill 40 thousandths off. That's equal to about 1 compression point, and you can mill a maximum of 130 thousandths off of a 2300 head, and that will take you right up to the intake manifold bolt holes. That's right up to here. You can't mill past that because you can't bolt the intake manifold on. Some engines, if you mill too much off the cylinder heads, you run into other problems with water passages and stuff like that. But that's not a problem on the 2300. You can take it right up to the intake manifold bolt holes, 130, and that should get you up to about 11.5 or 12 to 1 with a flat top piston. Okay, one other thing I failed to mention here. These are the dowels that are located onto the engine block. There's an equivalent hole for these two dowels. You just want to make sure when you do mill a cylinder head that these dowels, just pull them out and measure the depth of this hole and measure the depth in the block. Sometimes from different manufacturers, these dowels will be too long, and you'll think you're torquing or bolting the head down properly, but in fact it'll be bottoming out on the dowels. The stock factory head bolts, as they go in, do not have a problem. There's enough threaded area so that even when you mill a head 130, these do not bottom out on the block, and so that shouldn't be a problem for you. I mention it because our friends who are racing the older Pinto 2000, if you do mill the head on the Pinto 2000, one of the rear bolt holes, the bolt will be too long and the bolt bottoms out onto the block, and it gives you a false reading. You're not actually tightening the block, you're just bottoming it out on the block, and that's something that you have to watch out for on the old Pinto 2000. So that's our our reference back to that engine. All right, so that takes care of the bottom half of the motor, milling the head for compression. Now we're going to turn the engine over and we'll look at putting a camshaft in and going into valve spring stuff. So,
Okay.
Okay, next thing is cam bearings, if you've never seen them installed or whatever. Heads up here, we've knocked the cam bearings out, and boy, when this head goes through its life bouncing around the shop, if you drop it and it hits it hits these cam towers, you can pretty well throw the head away. They're somewhat fragile, and you just have to hope that they are not mishandled in wandering around the shop or anything like that. The cam bearings, they're all the same size, so the cam can either go out the front of the engine or the back of the engine. Guys who change cams on street-driven cars, sometimes they can just undo the motor mounts or take the radiator cap off and sort of jack the engine up a little bit, and the cam can slide out the front and still get out of the car. There's a lot of different situations there, so we can't cover everyone. To make a reference back to the old Pinto engine, it had an unusual, the old 2000 engine had 3 cam bearings, and they got bigger in the back, smaller in the front, so the only way you get the cam out was through the back. So when guys wanted to change cams on race engines, which we did too often, we used to cut a hole in the firewall so the cam could come right through into the car. So that was back then. Cams have advanced a little bit. Hopefully they don't fail as often nowadays. The cam bearings are all the same, front to back. The oiling hole is in the bottom. Again, that's the oil pressure line here, and it'll feed into the bottom of the cam towers and up through this hole in the bottom of each tower. The hole that you see on the top of the tower is to hold it for machining and has nothing to do with anything, really. You have to put cam bearings in with a cam bearing installation tool. It's a nasty-looking thing here, and I'm not going to bang one in, but we'll just show you. This is something you really want to have done at an engine machine shop, unless you have a tool or a friend like this who has the tool. It's again, not rocket science, but you just you tighten up on this and you get your hole lined up on the bottom, and what happens is this cone here centers everything, gets it in nice and straight, and you take some serious slams on the back here. You do those two, then you turn the head around and do the other two that way. This same tool would have been used to put the auxiliary shaft bearing in the block. So that's how that's done, and you really need to have that done that way. It costs you about $15 or $20 to have it done at a machine shop, and it's money well spent. They've got the tool, and let them do that for you. Okay, we'll shut off for a minute, and we'll get into valves and valve springs here.
All right.
Okay, a couple of different camshafts here. The early 2300s all came with what we would call a flat tappet cam, and then the later 2300s went to a billet roller cam. This is a cast cam, this is a billet cam. That they pour the mold. This one they start with a blank of steel, and with CNC machines and stuff they cut it out. The flat tappet cam uses a cam follower that looks like this. The lobe of the cam rubs against this surface, goes across the surface of the cam, and opens up a valve. We'll show you how that works in a minute. We have a second version of this, which is aftermarket version, in which a hardened pad is machined and then fitted with a high-strength epoxy type material, and this gives more reliability to a high RPM or a high lift camshaft, and that's come along as a result of a cam failure problem with the flat tappet cam over the years. So that's helped to make them a lot more reliable. The roller cam uses a cam follower like this. This comes standard in any roller cam motor, which would be all of your truck engines and the later 2300s in the cars as well. The roller on a flat tappet cam, the cam follower and the cam have to start life together, and that cam follower has to follow that cam all the way through. If you put in a new cam, you have to put in new followers. If you take the cam out of the engine for any reason to service it, you want to make sure that the cam follower stays with that cam lobe. So you got 8 of them. We usually put them on a piece of coat hanger and put a piece of paper that says 8 on the bottom, and we just stack them up like that, 8 to 1, so that when we put the things back on, we get them in the right order. And they have to stay together, and they have to be new with each cam. On the roller cam, that's not required. You can get a set of used followers out of an engine or buy new ones from us or whatever, but they can go on any roller cam. It doesn't matter. They're completely interchangeable, and it doesn't seem to affect the reliability. Roller cams are dead reliable. They just don't have problems, and they've taken all of the camshaft problems out of the 23. We would like to see all the racing organizations allow them just for that reason, because of their reliability. They are more expensive, but they give you a lot of peace of mind. So whether it's a street or a performance engine, consider that. Each of these cams has an actuating method, which can be, we offer, I think, 10, 12 cams for the 2300 for various lifts and various uses. Also in the catalog, they can be actuated by a hydraulic lifter, which is stock, which comes on every engine from the factory, or we make what's called a mechanical lifter. We call it a mechanical lash adjuster or a solid lifter, whatever you want to call it. And with this, you have to adjust with a wrench and do your setting with a feeler gauge. The hydraulic lifter is not adjustable. It just simply drops into the lifter hole, and your follower sits on top of it, pushes against the valve, cam fits in here. With the mechanical lifter, it's the same thing. We have a knurled edge on the top of them, so once they go in for good, and you tap them down, and they're in there for forever, hopefully. And you set your adjustment by screwing the top part up to set the adjustment, and then this is your lock nut here. So you would lock down against the base of it, and that holds this stud in the height that you're setting it at. When we have 2 versions of the solid or mechanical lash adjusters. The long version is used with stock length valves, and we use it with just one cam, which we call a stage 2 cam. And in that particular cam, we grind a smaller base circle so that it works. And the advantage of that is you have a mechanical cam. You don't have to do any machining to the head. You just take the hydraulic lifter out, put the solid lifter in, and you're ready to go with a mechanical lifter stage 2 cam. Our stage 3 and 3A cams, which are a higher lift cam, we use a shorter adjuster. And let me show you the difference between the two on the length. And it's quite a, hang on, it's quite a bit shorter, and about 1/4 of an inch shorter. And that's because we use a longer length valve in order to get a heavier valve spring, and we'll go into that in a minute. But when you put in the Type B, as we call it, this is the Type A lash adjuster. This is a Type B lash adjuster, the short one. You have to cut this boss down so that the top of the, you follow me with the camera okay? So the top of the lifter, or top of the mechanical lash adjuster is visible so that you can get the lock nut to lock down on it. And the lock nut locks down on this surface of the mechanical lash adjuster. So this surface has to stand a little bit proud of the base, because that's where your lock nut locks on. It does not actually lock onto the base. It locks onto the center of the adjuster. And we've dragged out a few adjusters here that have not been machined. This is a shorter one that hasn't been machined, and that would go into the hole just like that. And then you would have the lock nut would lock onto the bottom, and this is how you set your cam lash with a feeler gauge. We'll show you how to do that in a minute. Now, in order to cut this down, you need a tool. And the tool, we give you a pilot tool and a cutting tool that goes with it. The pilot tool just drops in there, and just for your own sanity, I tap this with a 3/8 or 3/8/16 tap. We just run a tap in there, get a few threads in there so you can get a bolt in there to get it back out. Otherwise, you go a little nuts otherwise. So the pilot tool drops in, and let's see, let me show you on the other head so you can see that it's you over with me, Brian?
Yes.
Okay, the pilot tool, see it's down there a good quarter of an inch or so. Now I'll screw this and get it back out again. Okay, the pilot tool back into this head, and what we did was cut it down with this cutting tool. And it's a combination cutting tool. You can just put a wrench, a drill on it, a 3/8 drill, and it'll just drill down on that outer surface until you get it to the height of the shorter adjuster. So the pilot tool is your guide as to the height, and it's not a problem if you go a little bit lower. That's all right, because you want the insert that you're going to put in there to stand proud of this base. So I'll put my threaded screw in there. And it's a fairly simple operation. You can do it with a 3/8 handheld drill. It's not very difficult. Run the drill slowly and not real fast, and it'll cut fine. Just use a little patience on there. It'll take you half an hour to do it. The adjuster that we would include, again, has the knurled edge on it. So do some measuring first, once you put that thing in there. And you'll be able to tap that down, and that'll be a permanent mounting of that adjuster. One minor point is that these do not feed oil or use oil, so you get a little more oil pressure up to the camshaft. If for any reason this thing started to turn and you're going to have it solid in there, you could actually drill a hole right through the side of the boss here and tap it with a tap, and then just put any kind of a bolt or a set screw through there to keep this from turning. But it should not turn with the knurled top on it, and it's going to be in there for the life of this engine. It becomes a mechanical lifter engine at that point. We have the depth, but we have the diameter we didn't cover. To get back to the original hydraulic lifter and the bore of the hole here. Once in a while, a cylinder head comes through from the factory where they had a problem with the boring of it, and they go to an oversized lifter. I'd say we've seen probably 5 of them in about 20 years. But if you get a head that you put a regular lifter in and the thing is slopping around all over the place, unfortunately you got one of those heads. And if you got one of those heads, I'd throw it away. It's gonna be a problem for the rest of your life. Try to find lifters for it. And they do make an oversized lifter, but they're hard to find, and none of our sod lifters will work on it as well. That's a very unusual situation, but once in a while it does show up. So those are the differences on the cams. You have the flat tapping cab, you have the roller cab, you have hydraulic lifters, and you have solid or mechanical lash adjusters. Now Paul's going to, we'll get this one head out of here. Yeah, I'll get it. Well, we're on the cams. When you get a 2300 head from the factory, it has that same cam plate that we used on the auxiliary shaft, and that's what holds the cam, keeps it from going fore and aft in the motor. And again, it's held on with those same Phillips head type screws with the star washer on it, right back here like this. Now, if you're changing a camshaft on the engine when it's in the car, you're going to have a rough time getting these screws out. And the only way that we've been able to do it, you put a short Phillips head screwdriver in here, and here's the firewall of your car right here, and you wedge some wood in there or something like that, and get a wrench on the screwdriver and try to break the Phillips head screws loose that way. Then you could take the cam out if it was still in the car, if you were going to change the cam without taking the head off. Now what we do on all of our race engines, just for our own sanity on this thing, is we take the plate, and which has the bevels for the Phillips head. We just turn the plate around for the flat side, and then we use either just use a regular hex Allen bolt in there so that you can get it out easily later on if you have to change it at the racetrack or whatever. Or you could use an Allen head bolt, either one, and that you could easily get to from the side. When you are changing these, this is the oil drain back that goes all the way down into the oil pan. So put a little piece of cloth or something there so that you don't drop everything down. It'll go all the way into the pan. If it goes into the pan, don't worry about it. Next time you change your oil, put a magnet in there, and you can it'll come out then. All right, so that's our basic overview of solid lifters and hopefully how to do it. I'm going to say one other thing. The same cutting tool is also used to cut the valve spring seat height, and we're going to get into that in a minute. And that's where your valve goes through, and that's where the spring seat sits, which I think I had one sat here, and the valve is going to come right up through there. And we'll use this to set the installed height of the valve spring, which is the distance between the bottom of the seat and the bottom of this valve spring retainer. And for various cams, you have to check that distance, and that'll be the next thing that we do. When you use this cutting tool, put a little oil on it, and especially when you're into the valve spring, into the valve guide, make sure that you oil it so that you don't heat it up and distort it. Okay, we'll shut off for a minute. Okay, we're going to go into setting spring heights on the head. And first, there's two types of valves that we use. When you use a stock hydraulic lifter cam or a stock replacement valve, it has a 4-groove keeper, and I hope you can see that there's 4 grooves. This is the stock length valve, and we sell a nice swirl polish version of it. We also sell what we call a cheater valve. It's exactly the same height, but it has a larger head on it for better flow for guys who are racing and are required to use a stock valve, but they want to cheat, so we give them that valve. We don't tell anyone who buys those valves. It's a big secret here. We're sworn to secrecy. These valves use the stock 4-groove keeper that comes with every 2300, and you put all right, we'll just leave that at that. The other valve is oversized valve that we use with our higher lift cams, and this valve is also a longer length valve, and I see that I've got it sitting here. All right, well, wait a minute. Let me go back and I'll show you how the valve sits on this head. The other one is already in the motor. The valves are just the keepers are angled down. Put the two keepers together. Retainer comes up, and that's what holds them on. Your valve spring is going to sit up there against the bottom of the retainer. I'll show you that in a minute. So that's how the retainer hangs onto the top of the valve. Now when you put the valve into the head, assemble a retainer just like we did on that valve, and this distance between the bottom of the retainer, right here where your valve spring sits, and the valve spring seat, where the valve spring sits in there, is going to be your installed spring height. That's the height that the spring is sitting with the valve closed, and that's all the way up. The valve spring will hold it closed. Now, there's a number of different ways that you can measure it. There's a thing called a height mic that is kind of an expensive tool that fits in there that you can unscrew. This is a machinist type of thing, a snap gauge, which you could put in there, and that sort of pops up, and you could do your measurement that way. And another way is with a dial caliper, and you can really come pretty close with a dial caliper using the, see if I can show it here, this piece that extends down. Put that on the in the bottom of the spring height. So you really get down here and line it up with the retainer, with the bottom of the retainer, so that this part is right up even with the bottom of the retainer. You'll get a pretty good reading from that. Just use your ingenuity on that. So here we have the installed height. Now, when we sell you a Type B valve spring and this longer, oversized valve, and I should mention that we put the keeper on the lower groove of the valve. This is actually a Chevy fuel-injected valves from an old Corvette or something, and they happen to have worked. And they're also 100 thousandths longer, which works with our Type B adjusters and the lift of the cam. There's a whole lot of trial and error before we got to this setup. This Type B valve, the keeper goes into the lower groove of the valve. You can't put it on the top groove of the valve because the retainer will hit against the, I'm sorry, the cam follower will hit against the retainer. I'll show you that in a second. But first we'll measure this thing. We've set this at 1.687. That's the installed height. If we needed more installed height, you would cut the valve spring seat deeper. If for some reason you were dealing with a situation when you had too much, you can buy a valve spring shim which goes underneath the valve spring to take up the space, but hopefully we get it right. So this spring and valve combination calls for an installed height of 1.687. I will show you how we do that. That's what we're going to call valve closed, 1.687, and we're going to say we're going to run a 540 lift cam. That's how much that valve is going to open. So the open dimension here is going to go down, just simple arithmetic, to 1.147. That's going to be the open pressure that's going to be put on this valve spring. Now, it's a single spring with a dampener, and we'll put it in a spring checker over here. There are a number of different checkers like this. If you don't have a way to check a valve spring, you can send it to us and we'll check it for you. It'll be okay. Now I've set this at my dial caliper at the 1.687. I'm just going to place that in on the spring checker and bring it down. And that's showing me right at 90 pounds here. We're 92 pounds. And that's really an ideal seat pressure. That's what we're looking at. Did I give the seat pressures yet? No. Seat pressures generally are 90 pads, and open pressure for a hydraulic cam is going to be around 200 pounds, and for our racing cams, we're looking for about 230, anywhere from 230 to 270 is acceptable. 230 to 260 is fine. Anything in there, you'll be able to buzz these as high as you want, and the valve won't float. The purpose of this is to keep the valve and the cam follower against the valve without flying around, because the spring pressure isn't stiff enough. So now when the valve is wide open at 540 lift, the valve spring is going to be 1.147, and I'm going to set this down to 1.147, and we'll see what the open pressure is. And that's what it's going to be at 540 lift. So if I bring that down, that comes right out at, let's see if we can get it right there. Comes right out at 240, and that's just fine. There's also a thing called coil bind. I'm going to have to stand on this for a while. Coil bind is when this spring is locked solid. And I'm going to say this dimension, which I'm not sure I'm going to be able to tell you. Do you know what coil bind is off the top of your head? It's the point. So it's under an inch. Is where the spring goes into complete coil bind. In other words, the spring is not usable at that point, and the rate on the spring will just go sky high. If you had a spring that coil bound, no matter what cam you had in there, it will destroy the cam immediately and have a lot of problems. So you want to make sure you don't have coil bind. Coil bind, you should have the spaces between all of these should add up to 1/10 of an inch, 100 thousandths. You could put a feeler gauge in there, but pretty much you can just visually look at the spring when you have it installed in the head, turn the cam over to make sure you don't have coil bind. You can do the same thing with it in the head. So that hopefully shows you how to set spring height. We give you the open and closed pressures for the springs and the recommended setting height for each of the springs based on the camshaft that you're using when you get them from us. And sometimes guys have different combinations. They've got a head from somebody and not sure what valves or valve springs they have in there. But generally, if you're around 90 or 100 pounds on the seat and you're between 200 open for a hydraulic and 240 or so open for a mechanical lifter cam, you'll be fine. You'll be able to run that as high as you want. Hopefully that covers valve spring and valve spring heights. Let me show you one more thing. Just let's see if I can get this one off. There we go. On the Type B spring and retainer, I just want to point out that you have to use the bottom groove of the valve. If you don't, you're going to be in trouble with when you use the bottom groove, which on a Chevy actually holds the oil seal, but on the Fords they work fine this way. Use the bottom groove. You have enough room for the cam follower to fit on there without the ears touching against the retainer. And at no time can the cam follower on any combination that you use touch the retainer. If it does, it will push against it, push it down, and tend to loosen it, and you'll lose. When this pops off, you're in big trouble, and then the spring will come off and the valve will drop down into the engine. If you were to put it on the top groove incorrectly, you won't have enough room. The cam will push the valve down and it will loosen the retainer, and the thing will come loose like that. So that's not so good. Better use the bottom groove. Okay, that hopefully covers installed height of the valves and how to do it. Okay, I've set up a cam in the 2300, and I put a couple of adjusters in, got the wheel on it, and stuff like that. And I want to show a little bit about the problems with timing a 2300 camshaft, and I'm going to use a V8, kind of an ugly V8 motor we have sitting here, just to give you an example. When you get a cam for a V8 motor, and V8 engine guys will call us and ask us, why are the numbers off on a 2300 cam? The V8s are very accurate. Your cam sits in the middle of the engine. The lifter sits in a nice straight barrel and pushes this push rod up, which pushes on the rocker arm. And I say this is a 1/6 or a 1/7 rocker arm ratio, and then it pushes down and opens up the valve. So if you had a 1-inch lift on the cam, you'd have a 1.6-inch valve lift. That would be a pretty big cam. But this is a very accurate system, and when you change rocker ratios from a 1/6 to 1/7, you see an increase in the lift of the valve. And when you get a cam for a V8, they come out on the button. They come out on the numbers. Unfortunately, the 2300, here we can pull this away now. The 2300 system is just not very accurate, and I want to point out why. Anyway, first of all, the center line of the cam is different distances from the intake valve, which sits here, and the exhaust valve, which comes up on the other side. Secondly, it's not really a rocker arm. People they say, what's the rocker ratio? Well, it doesn't really have a rocker situation. What it has is a lever arm in which the cam sweeps across across the pad of the cam follower. This is an average. They're averaging, it starts at one distance, and when it gets to the other end of it, it's further away from the cam than when it started. On the exhaust side, it's different again. So for a cam grinder, grinding a cam for a 2300 or any overhead cam engine is really challenging and kind of a nightmare to get it to come out right. So as you turn the cam should wipe across the follower, and we check to make sure that the pattern is right on the follower by putting some grease on the follower. Or you can use machinist blue, but just some grease on it, and that will show you that the cam is at least centered on the follower, and to make sure that you have your basic valve length right. This happens to be a 540 lift cam. We have our oversized valves. I'm just holding it up with my hand here, but that would be one simple way to check that. Now, we find that as accurate as you can grind the cam, when a guy puts valves in, he changes, possibly, they're all going to go in at a little different installed height depending on the machine shop that put the valves in. And the length of the valve will actually affect the opening and closing rate of the camshaft, and it will also affect the lift of the camshaft. So by nature, it's a somewhat inaccurate system. We simply don't feel it's worthwhile to degree in the cam. If you can get the cam to lift evenly and lift according to what we say, it's supposed to be a 540 lift cam, it should lift 540, we would put it on the engine at that point, and then from there I'm going to assemble an engine, put some clay on the top of under the valves, and we'll check valve to piston clearance, and I'll show you how to get the limits of advance and retard using retarding the camshaft using our adjustable sprocket, but and show you how to measure that so that you can assemble and reassemble an engine and get it exactly the way it was to start. So, all right, we'll leave it at that.